Hi folks, I thought I'd run through two kind of more challenging problems with you. One of them is a combination concept problem. And so what we have are really three concepts here. We have this purple block. I'm going to say it has a mass of, let's call it 2m, and we'll call this one m. And 2m, it's going to slide down a hill here of height y, and it's going to collide with m, and then that's going to, that system, we'll say it's an inelastic collision. They hit and they stick together. They'll then fall off this table and turn into, well, one of these horizontally fired projectile, and we want to find this delta x. Okay? So really three parts. The first part is the sliding down the hill. Well, that is a conservation of mechanical energy problem. All right, it's a frictionless hill, let's say. Right, and I would say that, well, let's see, KE initial plus GPE initial is KE final plus GPE final. Right, now for this part of the problem, let's go ahead and call this height 0. All right, that lets us get rid of this, and if we say it's released from rest, we get rid of that. Okay? So here's what we have. 2m GH, whoops, not HY, just Y. MGH is really 2m, that's our mass, G, and what we're calling Y, right, is 1/2 2m V squared. Well, notice the 2m's don't matter. And we can figure out that this thing at the bottom of that first ramp has a speed 2gy. Radical 2gy. Yeah? So that is when this thing is, well, I can't draw purple on this, but that's when it's right here. It's moving towards this other one. There's 2m. It's moving towards m at that speed. They then interact. And let's go ahead and qualify that interaction, I think we said that a minute ago, as an inelastic collision. Okay? Sure. So during the inelastic collision, we have M1 V1 initial plus M2 V2 initial is. I'm going to jump right to this if no one objects. Any objections? Oh, good. Right? They stick together, move at one common final velocity, inelastic. All right? I know that this one goes. Now I'm calling this object 1 and object 2. All right, so this really turns into 2m. Well, v of that one initial, remember, is this. Its speed at the end of sliding down here becomes its speed before it interacts with the other object. So we put that right in here, 2gy. Oh, you dig? Equals m1 plus m2. Well, that's, whoops, that's 3m. We have the 2m plus the m. Right? And now, what we get is that this system's final speed stuck together is 2/3 2gy. Now I feel like I dropped a 2 somewhere, but I don't think I did. Right, so why 2/3 of its speed before? Well, because now there's 3/2 as much mass. There were 2 units of mass, now there's 3 units of mass. So the speed is now 2/3 as much. Okay? Well, this now becomes this system's speed as it starts to do the horizontally launched projectile thing. So now we'll go the projectile thing. All right? It leaves this edge with a speed 2/3 radical 2gy. Right? Okay. Well, going back a few weeks, here's how we handle these. That's a x velocity. Here's the kicker, the big one. That's the big one. The initial vertical velocity of this projectile is nothing. We want to know what delta x is. The only way to find it is that. So we have to know time in the air, which means we're going to have to use the vertical direction stuff to find time in the air. Well, we know delta y is what we call h. We know a is g. These are both downward. And that's enough to write an expression, at least, for the time in the air. And we do it like this. V naught yt plus 1/2 gt squared. I hear you. Oh my God, I don't remember this. You probably do, or you will. That goes. And you'll recognize this. Only works for one of these horizontally launched ones. Well, we're calling our delta y h, right? Okay, we're almost there, because we have enough now to substitute. Well, let's see, what's Vx? It's 2/3 2gy times 2h over g. And we can simplify the heck fire out of that. Let's see, we got a g in a radical and a g in a divided by a radical. Those go. These two 2's under a radical multiply together to give us an actual 2. So that makes this 4/3. And what are we left with? All we have here is a y in there. Whoa, look at that. YH. I should have made you prove that. That's good. That's good stuff, people. Happens to work out that way for this problem. Kind of neat, huh? I think so. Now, I would never make you do that whole thing algebraically, but why not? More likely that you'd get numbers. I didn't feel like making up numbers. Okay? Okay. Fine. Fine. Well, so that's a multiple concepts problem. A good one to do. Another one I'd like to go over is another two-dimensional interaction question. All right. We've got an object here with a momentum like that. Oh boy, let's call this, I don't know, let's call it 100 kilogram meters per second that way. Let's say that this thing has a mass of, well, I don't want to get myself in trouble making up numbers just yet. Let's just make sure the things pan out right. And then afterwards, come on, where are you? Afterwards, I just am going to make up that this thing, the first one, recoils, we call that, bounces back like that, And the question is, what's the momentum of the other one? All right. So this is the delineation between before initial and after. So let's start with a conservation of momentum in each of two perpendicular directions. Okay? Let's try this. Let's try making this like M. You see that? I don't know. M. I don't know. 3M. Let's try that. I know for sure that if you shoot a less massive object at a more massive target, for sure the less massive one can recoil, like we've seen this. It can bounce backwards. All right, so let's just see what this other guy does. Well, right off the bat, here's what we can say. We know that this is 100 kilogram meters per second. All right? I'll try to get tricky here. Let's say that this recoil angle, what's that look like? About 60 degrees? Let's call it 60 degrees. What I would do is look at components of this one's final momentum. P1 final Y. P1 final X. I don't know if it's really 60. But I already said it, so I'm going to keep it. So let's say this is, let's call this 70 kilogram meters per second. All right, well, here's the deal. In the end, each one of these objects has to have some horizontal, some x direction momentum. All right? And so this is going to equal P1 final x plus P2 final x. And notice, we can now write expressions for the components of number one's final momentum. I could say the following. P1 final x is P1 final cosine 60. Right? Here's P1 final. Here's P1 final x. It's the x component. Right? Multiply by the cosine of the angle there. Okay with that? It's a vector component thing. So P1 final x is, oh yeah, 35. But it's 35 to the left. So that says that P2 final x is 100 kilogram meters per second minus P1 final x. All right, we started with 100 this way. We've got to end up with 100 that way. All we have is 35 the other way, so this one actually must be, well, 135. Yeah? Well, here's something neat to see. If we look at the y direction stuff, how much initial vertical, up and down, y direction, whatever you want to call it, momentum is there? There's none, right? This is all the initial momentum. None of it is up and down. Well, that means we have P1 final y plus P2 final y. And P2 final y is P2 final sine of 60. And I don't know what the sine of 60 is, but my calculator does. So if I do 70 sine 60, I get 61. P2 final y is 61. But notice it's 61 downward here, right? Downward. So I'm going to call that negative. And this says that P2 final y is negative P1 final y, or P2 final y is negative negative 61, or 61, of course. If number 1 gets 61 units of momentum that way, then number 2 must get 61 units of momentum this way. How good is my 135 compared to that? Not bad, not bad. Excuse me. I think we just concluded that this is 61. I don't think my math is too, or my scale is too good here, because that's, well, there's 60, 120. All right, maybe it's all right. Okay, so that's that. And then what we can do is, now that we know these two components of that object's final momentum, we could Pythagorean theorem them to death and find that total final. All right? Maybe whatever that is. I'll just do it. Why not? 135 squared plus 61 squared equals square root of that equals 148. No. Yeah? Okay. So what I want to show you is that there are instances in which using trig, we can calculate components, and have to calculate components of momenta. All right? But then really, why do we do that? So we can complete our summations of momentum in each of two perpendicular directions. Okay? Okay. That's it. Bye.